Welcome to ENE 480. This is part 3 of a 4-part series on statistical analysis of environmental data. In this unit, we'll discuss linear relationships between two variables. We'll look at linear regression, then look at confidence intervals for both the intercept and slope of that regressed line. And then we will look at predicting values of x and its confidence intervals from values of y. Now, throughout your academic career, I'm sure you've observed how two variables of an experiment appear to be related to one another. For example, the height of an object versus its shadow length for any given time, day, location, the distance traveled versus time, assuming constant speed, of course, flow rate versus velocity for constant area of a pipe flowing full, and pressure gradients versus fluid density. Three common linear relationships you will encounter in this course are calibration curves, which relate the concentration of a substance to the color imparted by a dye, a titration curve, where the volume of a titrant, in our case the number of drops, is related to the concentration of an analyte, and first order rate expressions, where the log of the concentration of a substance is related to the reaction time. Shown here are several graphs that show the relationship between two variables. If we look at this upper left graph here, we see that there is a strong positive correlation between variable x and y. On the other hand, if we look here at the upper right-hand graph, we see that there is a strong negative correlation. On the opposite end of the spectrum, we can look at the data in the lower right-hand figure, and we see that there is no correlation between the values of x and y. Now, for the others, we have a weaker, either positive or a negative correlation, but it's harder to tell the strength of those relationships. So that's where statistical analysis comes in. So let's first look at calibration curves. The approach here can be used for first order rate expressions and other linear relationships as long as the assumptions are valid. So the assumptions we're going to make here is one, that y is linearly related to x. Done this since you were in grade school, and you have an equation that y is equal to, and the equation you will use is a equals bx. So a being the y-intercept and b being the slope. Now, we also assume with these calibration curves that the x values are accurately known, or at least the errors in those values are much smaller than those associated with the y values. Time also usually fits this criteria, as it can be measured accurately. We'll assume that the errors associated with y values are independent and homogeneous over that range of y values. We're assuming that that range of y values belongs to the same population. And those errors have an average value of 0. So that means that there's no positive or negative skewing in that error. They're random errors, and that the data are normally distributed. So let's look at a first example, and in this case, we would be doing this if we were in the lab this semester. But in this case, what we're looking at is we're looking at obtaining calibration data from a turbidity meter. So we're measuring turbidity of a water. In order to be able to do that, we need to have standards In this case, these are standards for which we know the solids concentration in parts per million, and we have a scale reading that is related to each of those solids concentration. So we have that data. We've generated the data for the calibration curve. We then can plot that data. So we're plotting this data as our instrument reading versus the solids concentration. Looks like we have a pretty nice straight line here. And what we would do is we would do a linear regression in order to find the best fit line. So what your linear regression is doing, or what we're doing in this process, is we have a predicted line and we're looking at what we call the residuals. So this is the difference between the data that we generated and the best fit line. And your linear regression line is the line where the square of these residuals is the smallest sum possible. We also use R squared. It's also called a coefficient of determination, and it is a goodness of fit measure that we use for linear regression models, and it indicates the percentage of variance in the dependent variable that the independent variables explain collectively. So our independent variable is x, and our dependent variable is y. So it's the variance explained by the model, okay, divided by the total variance, and it's generally a fractional value. Excel makes this very easy, and all that's happening is basically this regression analysis is done by Excel. And if we do this on our calibration data, what we end up with is a calibration curve, and we end up with a linear best fit line and an R squared. And we see we have a very nice R squared. The closer that is to 1, the better fit. Perfect fit would be 1. Rarely you will ever see it. And our slope in this case is 117.29, and the y-intercept is 2.025. Now, we previously looked at calculating the confidence intervals for the mean value of a data set. In this case, what we're looking at doing is calculating the confidence interval for the slope, for the intercept and the slope. As we've done before, we will use the student Ttest, and all of the necessary equations are given here. So we have an equation for A. So this is the calculated value from the regression equation, and this is our confidence interval. Now we have standard deviation, variance on X, and we have a variance on Y, and this is the variance of Y on X. And then we have a slope. So this is the slope from that regression line. And then we have a confidence interval that we will calculate. So let's look at an example, our example. So we've mentioned we've generated this data. And we can use Excel to calculate the mean, calculated the sum of all of our X values, and the sum of all of our y values. This is the sum of the x values squared, the sum of the y values, and the variance on x and the variance on y. Now, we'll do a two-tailed t-test again. So again, this is a two-tailed t-test table. So we're looking at the 95% confidence interval. So alpha here is 0.05. The number of observations that we've made is 7. So in this case, the number of degrees of freedom is equal to n minus 2, or 5. So we've got 5 degrees of freedom. And we have a critical t-value. So the critical t-value that we calculate from the table is 2.571. Now, we can go through and we substitute in the values for all of the equations that you've been given. So we have a standard deviation, y on x. We have substitute in here. So we have a standard deviation on our y-intercept. So notice our y-intercept standard deviation is plus or minus 5.88, which actually means that we have a range from about a -3 to a positive almost 8. And then we have the standard deviation on the confidence interval on our slope. And you can see that that is 13.28. So our slope can range from 117.29 plus or minus 13.28. We can do the same type of analysis in Excel. Again, you should have the data analysis tool set up on Excel. You will use the regression statistics. So there's a function, regression statistics. You want to use that. Okay, it will give you the r squared for your equation. You'll notice it's the same r squared that we obtained from the regression line. And what you're looking for is the data right here. Okay. So this gives you the lower 95% and the upper 95% on the intercept, and then it gives it for the slope. So you can see that's the intercept ranges from about -3.9 up to almost 8, 7.9, and our slope ranges from 104 up to 130. What that means, okay, is that if we were to run this any random set 100 times, 95 times, we would obtain a slope that would be between 104 and 130.6. So next thing we need to do is we need to determine an x and the confidence intervals on that x from y. So we're going to predict this from a value of y. Okay, so continuing with that example, the example that we've just been talking about, you've run your calibration curve. Now you have an unknown. So you've got a sample from the Red Cedar River. You place it in the turbidity meter and you obtain a reading of 60. Now you need to know what's the solids concentration that corresponds to that reading. So we will use the equations that have been given, and we've calculated our slope, our intercept, we've calculated the confidence intervals. Now what we want to do is we want to determine that solids concentration that corresponds to the scale reading of 60, along with the confidence interval for that concentration. Again, we'll use the two-tailed t-test. We're using the calibration data that we generated. So we had 7 observations. Degrees of freedom is still n-2, so that's equal to 5. And we're looking at the 95% confidence interval, so the alpha value is equal to 0.05. Thus, we have a critical t-value of 2.571. So substituting into the equations that have been provided, we determine that the standard deviation of y on x is 3.14. We then substitute into this equation here. The value of y is 60, so we can substitute that. A is your intercept, B is your slope. This t is the value that we just determined, the 2.571. The standard deviation of y on x is given right here. Substitute the rest of the terms in, and what we find is that the concentration that corresponds to a scale reading of 60 is 0.49 plus or minus 0.56 parts per million solids. So you not only have the concentration, but you have the confidence interval at a 95% level. So you can be, if you were to measure this sample 100 times, 95 times out of that 100 times, you would find that the concentration is between, or is within this range, from 0.49 to plus or minus 0.56. So from this lecture, we've looked at determining regression lines, R-squared, we've looked at how to evaluate that, and then we've determined confidence intervals for the intercept A and the slope of B. And then we've looked at predicting values of x and the confidence intervals for that value of x predict from a value of y. And for more examples on how to determine the confidence interval for the slope of a regression line, I provided you this link here, and hopefully that will assist you further. Thank you, and have a great day.